Okay, this is section 7.3. 7.3 is pretty much all about a dozen or so formulas to learn. The double angle formulas, half angle formulas, power reducing formulas, sum to product, and product to sum formulas. So a whole bunch of formulas to learn, at least a dozen new formulas just in this section. So I'm going to follow what the textbook, the order the textbook teaches them here. So first, double angle formulas. Double angle formulas. What this means is if we've got some input of an angle that's been doubled here, so that's double angle formulas, then we can write it in terms of sines and cosines of an input that has not been doubled. Alright, so cosine of 2x. So there's sine of 2x, and then cosine of 2x has a few different formulas here. So there's one of them, and then another representation is 1 minus 2 sine squared x, and then 2 cosine squared x minus 1. These are all coming straight from the sum formulas from last time, because we can write 2x as x plus x, and I'll show you at least one of those. I'm not going to prove every single one because they all kind of go the same way. 2 tangent x over 1 minus tangent squared x. I think the book walks through one of these two, so I'll just quickly prove. I'm not going to prove all the formulas, but these double angle formulas follow really nicely from the formulas from last time. So if I say proving this formula, what I'll do is I'll say tangent 2x is equal to tangent of x plus x. And then I have a formula for a sum inside of my tangent, and it is, what is it? It is tangent of x, oh man, I forgot it. Plus, is it plus? Yes, plus tangent of whatever the second variable is, but here it's also x. And then in the bottom, 1 minus tangent of x times tangent of the second variable, but it's also x. And then this is tangent x plus tangent x. They're the same, so that's 2 tangent x. And similarly here, tangent x times tangent x is going to be tangent squared x. And there we go. So there's the identity for tangent. And they pretty much all go the same way for sine of 2x and cosine of 2x. You're just replacing 2x with x plus x, and then following from the formula for this situation. Alright, so let's do some practice with these. So let's say for part A, if cosine of x is equal to negative 2/3 and x is in quadrant 2, find cosine of 2x and sine of 2x. So we know cosine of x, but we want to know cosine of 2x and sine of 2x. Okay. Sorry, one second. Okay, yep. So if we're looking at the cosine of 2x formula, so I'm going to find this one first. I know that I'm going to need, which can I use? I can use this, 2 times cosine squared x minus 1, because I already know cosine x. Whoops, I already know cosine x. So I can go ahead and plug straight into this formula, because I've already got cosine x. So I'm going to say cosine of 2x is equal to 2 times cosine squared x minus 1, but that is negative 2/3 squared. So this square means square the entire cosine of x. So there it is. Minus 1. There's the minus 1. And then this is This is 2 times 4 over 9, which is 8 over 9 minus 1, so I'm getting negative 1 over 9. Okay, there's that one. Now, sine of 2x is not quite as easy because sine of 2x requires me to know sine x and cosine x. I've got cosine x. Cosine x is negative 2/3. But I need to find sine x because this is 2 sine x cosine x. But I need to find sine x. So that's why they gave us this information. I know that x is in quadrant 2. X is the angle here, by the way. They chose to use x as the angle in this problem. And I think in all the problems in this section. And I know that cosine x is negative 2 over 3, so that's adjacent over hypotenuse. So I need to find this side using the Pythagorean theorem. So I'll say 3 squared is equal to negative 2 squared plus b squared, calling this side b. That's going to give me b is equal to square root of 9 minus 4, so square root of 5. So I'm getting this as square root of 5. That means that sine x, which is what I needed this triangle for, is square root of 5 over 3. Square root of 5 over 3. Okay. And it's positive because I'm in quadrant 2. Okay, so now I've got sine x. So I can say 2 times square root of 5 over 3. And then cosine x is given as negative 2 over 3. And then just a little bit of fraction arithmetic, getting negative 4 square root of 5 over 9. Okay, let's do another one. Okay, example 1b, I've got given that tangent of x is negative 4/3 and x is in quadrant 2 again. Find all three of these trig double angle functions. So let's find tangent 2x, sine 2x, cosine 2x. Okay, well, tangent 2x is going to be easiest because tangent 2x uses just the tangent x function, and I've got tangent x, so I'm going to go ahead and get that one out of the way. Tangent 2x is equal to 2 times tangent x over 1 minus tangent x squared. And that is 2 times negative 4/3, just replacing tangent x with negative 4/3, over 1 minus negative 4/3 squared. That's going to give me negative 8/3 in the top, and then over 1 minus 16/9. Okay, negative 8/3 all over 1 minus 16/9, that's going to be, well, this is 9 over 9, right? This is 9 over 9. So 9 minus 16 is negative 7 over 9. Okay, and then that is equal to negative 8/3 times negative 9 over 7, is fraction division. And then I'm getting 72 over 21. Let's see. That's... Oh, I can simplify. There's a factor of 3. Let's see, there's a factor of 3 in both of these. This will give me 24 over 7. There we go. Okay. Now, for the other two, for sine of 2x and cosine of 2x, I know I'm going to need to know what sine and cosine are. Now, cosine of 2x only requires that I, at the very least, know at least one of them. But since I need to know sine of 2x as well, and I need both of them for that, I might as well just get both of them right now. So let me draw my triangle in quadrant 2. So I'm orienting it so it's in quadrant 2. Here's my angle x. Well, actually, I suppose x would... Well, anyways, this is fine. Okay. So, no, yeah, that is where x is. If tangent x is negative 4/3, that's opposite over adjacent. So I've got a 4 and a 3. Now, when I write the fraction negative 4/3, that just means the entire fraction is negative. That doesn't tell me which one of these numbers was negative from the triangle. But since I know I'm in quadrant 2, I know that this one is negative. Okay. Now, Pythagorean theorem. This is actually one of those common triangles, a 3, 4, 5. So just by knowing that, I don't need to actually run the Pythagorean theorem. Alright, sine of x then will be opposite over hypotenuse, and cosine of x will be adjacent over hypotenuse. Now I can find, let's see, I'm going to try to do it here. Sine of 2x is 2 sine x cosine x, which is 2 times that fraction, 4/5, times that fraction, negative 3/5, which is going to give me negative 24 over 25. Okay, and then cosine of 2x, which I guess I will come over here to do. And now I have some options with cosine of 2x, but I'm just going to keep it easy on myself, and I'll do this one. 1 minus 2 sine squared. So 1 minus 2 sine squared of x, it's going to be 1 minus 2. Sine squared will be 4/5 squared. Did I write these formulas down wrong? Because I got something different earlier. I think I just plugged it wrong. Okay, this is fine. Okay, 1 minus 2 times 16 over 25, that's going to be 32 over 25. And that's going to be equal to negative 7 over 25. Right, let's see, 25 over 25. 25 minus 32 is negative 7. There we go. Okay. Okay. Okay, example 2 says... So a different way of using the double angle formulas now. Write cosine of 3x in terms of cosine x. So we want to get rid of any input of 3x in here. We want to get rid of the 3 and just have it in terms of cosine. Okay, well, I know that cosine of 3x, I don't have a formula for that, but I know that I can write it as cosine of 2x plus x. And I do have a formula for a sum inside of a cosine from the last section. And that tells me, well, what's going on here? What did we use? We used x and y. Well, this is playing the role of the first variable, and this is playing the role of the second variable. So it should be cosine of first times cosine of second minus sine of first times sine of second. Okay. And now, coming from over here, I have formulas for both cosine of 2x and sine of 2x. And they tell me to write everything in terms of cosine. So let me pick this one so that I'll have just a cosine involved. It's cosine squared, but hopefully it'll work out. So let's see. This is getting replaced with 2 cosine squared x minus 1. That's that. And then times cosine x. minus, now sine 2x, I only have one option for that. It's 2 sine x cosine x times sine x. Oh, I see. Okay. Then we're going to have, that may not have been the best choice here, because 2 cosine squared x minus 1 times cosine x minus 2 sine squared x cosine x. So all I did between here and here is I multiplied sine x times sine x. And now I'm seeing that I can factor a cosine x out, leaving me with cosine x on the outside, and then 2 cosine squared x minus 1 minus 2 sine squared x. Okay, and then I'm going to do something weird here where I say that, let me think for a moment. Well, one thing I can do that would completely get rid of sine squared is use the Pythagorean identity that says sine squared x plus cosine squared x equals 1. So sine squared x is equal to 1 minus cosine squared x. So I can replace that. So I'll have cosine x times 2 cosine squared x minus 1 minus 2 times 1 minus cosine squared x. And then surely this can be cleaned up a whole lot. Let's see, cosine x, and then 2 cosine squared x minus 1 minus 2, distributing the 2 in, and then plus cosine squared x. Okay, and getting cosine x times 2 cosine squared x plus cosine squared x is 3 cosine squared x. And then minus 2 minus 1, that's minus 3. And there we go, it's all in terms of a cosine now, and I can go ahead and distribute and say 3 cosine cubed x minus 3 cosine x. Oh wait, dang it, this is supposed to be a 2 there, because I distributed a negative 2 in there, so that should be a 2, meaning this should be a 4. Alright, final answer is 4 cosine cubed x minus 3 cosine x. And actually, any cosine given as like cosine of some number times x, like cosine of nx, can always be written as some in terms of cosine with the nth power of cosine. So it'll be like some polynomial kind of, but with cosine of x instead of just x's. So something like, so we don't know the coefficient attached up front necessarily, but cosine n of x plus, you know, other powers of cosine, but the highest one, the leading one, the number here will match the degree, which is kind of interesting. Okay. Example 3. More using double angle formulas. Prove the identity. Let's say, which one did the book do? I think they did that one, so I'll do tangent of 3x equals 3 tangent x minus tangent cubed x all over 1 minus 3 tangent squared x. Okay. We're going to be working with this left-hand side, trying to get the left-hand side to look like the right-hand side, because there's really not much. There's a lot going on here, but I would be wary of working with this we just have more to do over here because there's more to expand. So just working from the left-hand side, tangent of 3x with a similar technique to the last problem can be written as tangent of 2x plus x, and that can be written as, let's see, that can be written, I've forgotten my sum formula. There it is. No, that's not it. Oh yeah, okay. It's the sum of them in the top, tangent of 2x plus tangent of x, all over 1 minus the product of them, tangent of 2x times tangent of x. There we go. Okay, and then, save space, I'm going to work from here. Tangent of 2x is that, 2 times tangent of x over 1 minus tangent squared. So we're going to have fractions inside of fractions, so let's be careful here. Here's my big fraction bar. Now I'm writing tangent of 2x. That's going to be 2 times tangent x over 1 minus tangent squared x, and then plus tangent x. There's my numerator. Then 1 minus tangent 2x, which is this thing here. So 2 tangent x over 1 minus tangent squared x, and then times another tangent x, which I can go ahead and throw up here. Okay, now we got to figure out some algebra to do on this to get it to look like this. It shouldn't be too bad. Let's get a common denominator in the top and a common denominator in the bottom. So 2 tangent x, my common denominator in the top will be 1 minus tangent squared x. Oh, am I going to regret doing this? Nah, it'll be fine. So the left-hand one is fine, 2 tangent of x. That already had the denominator. Plus. Now this needs to get multiplied by this. So I'll say, because I'm getting that common denominator here, 1 minus. Okay. So I'll handle that expansion in the next step. Now in the bottom here, I've got a 1. Now my common denominator is actually going to be the same, 1 minus tangent squared x. Now if this was a 1, then this 1 needs to get multiplied by that, so it has the same denominator. But that's easier. That's just going to be 1 minus tangent squared x, and then minus 2 tangent squared x. So what I did there is I went ahead and said tangent x times tangent x is tangent squared x. Now I can write this giant fraction as the first fraction times the inverse of the second fraction. So it's going to be the first fraction times the inverse of the second fraction. So the first one is going to be, 1 minus tangent squared x is in the bottom. And I can clean up the top a little bit. I'm going to have 2 tangent x, not distributing this tangent x, plus 1 tangent x, minus tangent cubed x. That's looking good because I'm supposed to have that up top over here. And then times the inverse of this fraction. So I put that denominator up top. That works because these are going to cancel each other. That's nice. And in the bottom, I can clean this up a little bit and say 1 minus, negative 1 tangent squared minus 2 tangent squared. That's going to be 3 tangent squared x. Alright, these two cancel each other. And I'm left with 2 tangent x plus tangent x. That's going to give me the 3 tangent x, and then minus tangent cubed x. And in the bottom, I've got this 1 minus 3 tangent squared x. So we get right to where we want it to be. Lots of algebra techniques coming in. Okay. All right. That is it for double angle formulas, I think. Yeah. Next thing is formulas for lowering powers. In other words, going from high powers of cosines and sines, like sine squared, cosine squared, and tangent, to just in terms of sines and cosines and tangents. These are really useful in calculus. Later, when you try to do calculus operations with things like sine squared x, you're going to find that it's going to be much easier to know that it can be written as 1 minus cosine of 2x over 2. Or similarly with cosine squared x, we can write it as 1 plus cosine 2x over 2. Cosine is a popular trig function. Tangent squared x can be written as 1 minus cosine 2x over 1 plus cosine 2x. And that's just coming from sine over cosine. So this over this gives me this. The 2's cancel each other. And anyways, okay. I'm not going to prove any of these. It wouldn't be too hard. You would work from this side and use the double angle formula. It would actually work out really nicely. And then you could prove this one the same way. And then for tangent, just say, well, tangent is sine over cosine. So plug, if tangent, then tangent squared is sine squared over cosine squared. So you'd plug this in over that. It would all cancel, and you would get this. So not really worth it to prove those. Nothing new coming from that. So let's just practice using the example 4. So let's express, sine squared x, cosine squared x in terms of first powers, so degree 1 of cosine. Okay, so sine squared x, cosine squared x is equal to, well, sine squared x is 1 minus cosine 2x all over 2, and cosine squared is 1 plus cosine 2x all over 2. So we're going to do some distribution here. Denominator will be 4, 2 times 2. Now here I need to do some distribution, so 1 times 1 gives me 1. 1 times positive cosine 2x gives me positive cosine 2x. Moving on to the negative cosine 2x times 1, that's going to give me negative cosine 2x. And then I'm going to have negative cosine 2x times cosine 2x, that's going to give me negative cosine squared 2x. So it's cosine 2x times itself, and it's negative. And by the way, these are going to cancel, aren't they? So cleaning this up a little bit, I've got 1 minus cosine squared 2x all over 4. But I'm supposed to write it in first powers, or in terms of first powers of cosine. So what I can do is I can use this formula again. But what's going to happen here is I'm going to have 1 minus something all over 4. It's going to be this, right, because I've got cosine squared. But look at what happens to the x here. This input is just an x, and then it gets doubled here. This is a 2x. It needs to get doubled. So instead of 1 plus cosine 2x, I'm going to have 1 plus cosine 4x all over 2. So that's because I've got cosine 2x squared. Okay. So if this was cosine of 6x, cosine squared of 6x, then over here you would write 1 plus cosine of 12x all over 2. Whatever is in the input gets doubled. Now the 1 and the 2 in the fraction, they stay the same though. Alright, so this can be cleaned up a little bit. We can say, what can we say? We can get a common denominator in the top. which would be 2. So 2 minus, can go and distribute this minus sign, 1 minus cosine 4x. So I did a couple things there. I got a common denominator with this 1, just 2 over 2, and then went ahead and distributed this minus sign. And then that's going to be 1 minus cosine 4x over 2 times 1/4. There's the inverse of 4. This is 4 over 1, right? So divided by 4 is the same as times 1/4. So finally I'm getting 1 minus cosine 4x all over 8. All over 8. Cool. Alright. Half-angle formulas. So those power-reducing formulas are important in calculus, but they're not really the focus of this section, so that's why I only did one example with them. Okay, half-angle formulas, though, are pretty important. They're a little bit weird. Okay, sine of some angle in half is equal to plus or minus, these are probably the weirdest formulas, 1 minus cosine u all over 2. Then we've got cosine of u over 2 equals plus or minus square root 1 plus cosine u all over 2. I'm going to explain a little bit about these after I get them written down. And tangent of u over 2 is 1 minus cosine u over sine u, or we have options for tangent, sine of u over 1 plus cosine u. So what's happening here is these formulas are for, well, they're for a number of things, but I suppose the main use of them is if you've got half of some special angle that you know about, that's when you use the half-angle formulas. So if you know some special angle, like 30 degrees, that's a special nice angle, but you've got, sine of 15 degrees, then you would let u be 30, because 30 over 2 is what you have, 15, and then you would plug in to, you would use 30 in the formula. By the way, the plus or minus in these two is determined by, not by where u is, but by where u over 2 is. Okay. Alright, let's do an example using these. We're actually going to do a few examples. Find the exact value of sine of 22.5 degrees. So you look at this and you say, I can't find the exact value, it's not a special angle. But then you realize, wait a second, you have to realize that 22.5 degrees is half of 45 degrees, which is a special angle. So let u equal 45 degrees. You let u equal the special angle, the actual angle that you know about. And then you're saying sine of 22.5 degrees is equal to sine of 45 degrees over 2. So there's the setup. U is now 45 degrees. U is 45 degrees. Go away. Okay. Sine of 45. Okay, so now I can say plus or minus square root of 1 minus cosine, there we go, 45 degrees all over 2. Now, where is 45 degrees? No. Let's see. I'm trying to figure out the sine, so I need to ask the question, where is 22.5 degrees? Well, that's in the first quadrant. Sine is definitely positive, right? Because 22.5 degrees is like there. Sine is definitely positive there. Everything's positive in the first quadrant. So So I can drop the plus or minus and just say square root. And then I'm going to have 1 minus. Now cosine of 45 degrees is square root of 2 over 2 and then all over 2. So this whole thing is under a square root. Alright, so we determined this was positive. Alright. This is all under the same square root, so if we get a common denominator in the top, we'll have 2 minus square root of 2 all over 2, and then all over 2, which is going to give us square root of 2 minus square root of 2 all over 4. And then that's going to be, can pull that 4 out, but it's in the denominator, so it'll be 1/2 square root of 2 minus square root of 2, which is a bit weird. I've got a square root buried in a square root because of the square root from the formula and the cosine of 45 that yielded a square root in the answer. That's fine. Just means it's a really irrational number. Alright, let's do part B for that. Just another problem. Find the exact value of tangent of 15 degrees. So we have to figure out what angle this is half of, what special angle this is half of, and I think pretty clear that u should be 30 degrees here. U is going to be 30 degrees. So I'm going to say tangent of 30 degrees over 2, which is what I have, tangent of 15 degrees, is equal to 1 minus cosine of 30 degrees all over, wait a second, okay, all over sine of 30 degrees. I guess if I'm using parentheses. Okay. But I don't know what cosine and sine are for 30 degrees. Well, yeah, I do. Those are special angles. So this is 1 minus, by the way, this is all in the first quadrant, right? 15 degrees. 15 degrees is definitely in the first quadrant, so these are both positive. What is cosine of 30 and sine of 30? I gotta draw my reference triangle. Okay, so cosine of 30 is square root of 3 over 2, and then sine of 30 will be 1 over 2. So this is going to be the same as 1 minus root 3 over 2 times, well, actually I can get a common denominator. It's fine. Times 2, the inverse of this. I've got divided by 1/2, that's the same as times 2. I can go ahead and distribute the 2. Yeah, that's fine. I'll distribute the 2, and I'll have 2 minus square root of 3. The 2 times 1 is 2. 2 times this cancels that 2 in the bottom. Okay. Example 6. Still doing half angle. For the next 3 examples, we're going to be doing half angle stuff. Okay, find tangent of u over 2, so they don't give us an actual angle here, if sine of u is equal to 2/5 and u is in quadrant 2. Okay, so, this symbol, I was using that in my notes that I have over here. This means, this is like saying in. Usually it's for sets, like you could say like x is in the real numbers. I don't know if you've seen that before. I may have shown you that before, but this is just kind of my shorthand way of saying that the angle is in quadrant 2. Okay, so let's see. We want tangent of u over 2, and we've got sine of u over 2. Tangent of u over 2 involves sine and cosine. So I need to find cosine of u. But that's why they told me u is in quadrant 2, and that's why I have this information. So quadrant 2 is oriented this way. If sine of u is 2/5, that means the opposite is 2, and the hypotenuse is 5. Leo, Okay, and my missing side will be, let's see, what would it be? Square root of 21, just by Pythagorean theorem. And it's it's negative, because we're in quadrant 2. So cosine of u is equal to negative square root of 21 over 5. Alright, plugging into my formula now, I've got tangent of u over 2 is equal to 1 minus cosine of u, which is negative square root of 21 over 5, and then over sine of u, which is 2/5. Okay, and now cleaning this up, I shouldn't have squished it there. I'll start from over here now. I'll have 5 plus square root of 21 all over 5, getting a common denominator in the top. And then times the inverse of 2/5. There's lots of quick algebra happening in these. If I wrote out every single step with this algebra, it would take a lot longer. So the quicker that we get comfortable with doing little algebra things like just going ahead and writing this 2/5 is times 5/2 and things like that, it's going to make these problems seem easier. Less room for mistakes. I guess that's debatable because we're skipping steps. Anyways, these 5's cancel. We get 5 plus root 21 all over 2. It would be funny if I made a mistake in this as I said that. No, that should be fine. Okay. 6, 7, 8. That was example 6. Example 7, still half angle problems. We're going to write sine of 2 cosine inverse of x as we did a problem like this last time as an algebraic expression in terms of x. Algebraic expression. Terms of x. By the way, x is between, just to keep it in the domain of the inverse cosine, x is between -1 and 1. Well, just like we did last time with a problem like this, first thing you want to do is call this thing an angle. Give it an angle name, because it is an angle. The output of an inverse trig function yields an angle, so let's go ahead and name it an angle, just for the notation's sake, just so we don't go crazy trying to follow this notation around. So what I have here is that sine of 2 cosine inverse of x is equal to sine of 2 theta, which is good because now this looks much more manageable because I have a formula for this. Wait, this is not a half angle problem. This is a double angle problem. I may have gotten out of order. Anyways, okay. So I guess this is a double angle problem. Sine of 2x or 2 theta is 2 sine theta cosine theta. And we want to write these back in terms of x. And I do know that from this way I've defined theta that cosine of theta is equal to x. So I've got cosine theta, but what is sine theta in terms of x? I don't know, but I can draw my triangle. And I'm not worried about the quadrant. When they give me an x, the x is going to have any information about the sine wrapped up in it, so I don't need to worry about the way I orient my triangle. But I do need to know that if cosine of theta is x, and this is theta, then this is adjacent over hypotenuse, so I must have x and 1 there, and that means that this side, by the Pythagorean theorem, will be 1 squared minus x squared, or just 1 minus x squared, or I should say square root of 1 minus x squared. That means that sine of theta will be opposite over hypotenuse. There we go. Because the hypotenuse is 1, so it's just this over 1. So I'm not writing the over 1 part because it's redundant. So now this, little star there, I'll pick that equation back up, is 2 times sine theta, which is the square root of 1 minus x squared. Maybe I'll wrap that in parentheses, and then times cosine theta, which is just x. And that's it. I mean, I guess I can rewrite the 2x times square root of 1 minus x squared. Can't really be cleaned up much more than that. Okay, example 8. Evaluate. Okay, these are double angle things. I thought we were going to be doing more half angle things, but I guess I just forgot the order of the examples. Evaluate sine of 2 theta, where cosine of theta is equal to negative 2/5, and theta is in quadrant 2 again. So this is very similar to this problem. It's just that instead of saying x here, they're giving us actual numbers. Like instead of making us name cosine inverse as theta and then figuring out that cosine theta is x, they're just straight up telling us that cosine theta is a number. It's still going to be kind of the same thing though. We're going to start with sine of 2 theta, write it as 2 times sine theta cosine theta. And we're going to say, oh, we have cosine theta, so we need sine theta, so we draw our triangle. This time the orientation of the triangle does matter though, because it's not some arbitrary x, it's actual numbers. So from cosine theta being negative 2/5, I know that my adjacent side is negative 2. This is theta here. And my hypotenuse is 5. And then by the Pythagorean theorem, this will be square root of 21. I'm skipping all these Pythagorean theorem because I'm assuming you've got that. You can do that on your own. So now sine of theta, which is what I needed, is opposite over hypotenuse. And then that means that this is 2 times square root of 21 over 5 times negative 2/5, because cosine theta is negative 2/5. And that's going to give me negative 4 square roots of 21 over 25. Okay. Now we've got 4 more formulas. They're called product to sum. And they can be derived fairly easily from previous formulas. Sine of u times cosine of v is equal to 1/2. You know, I've been following the textbook and the way they write these formulas down, and they keep jumping around between x, y, theta, phi, u, and v. I don't know why. I've never seen a single textbook jump around so much. It's strange. Okay, u plus v. Maybe they're just trying to get you used to different notations. Okay, so if I've got the product of a sine and a cosine, which we've seen these things before, we've seen them all over the place in our formulas, that's the same as half of sine of u plus v plus sine of u minus v. Then cosine of u times sine of v, so just kind of swapping roles here, is 1/2 times sine of u plus v minus sine of u minus v. Is that? But these might as well be the same, because it's just sine times cosine. Sine times cosine. It's just that the u and v is swapped. So if you swapped u and v, oh yeah, if you swapped u and v here, that would you would be able to factor a negative out, and sine is an odd function, meaning that if you factor a negative out of these two, you could pull it all the way out of sine, and that would make this negative. Okay. I don't really feel like these need to be two separate formulas, but that's okay. Alright, then the last two, cosine of u times cosine of v, so the product of two cosines with different inputs. This is not cosine squared, because these are different inputs. That's 1/2 times cosine of u plus v plus cosine of u minus v. And then product of two different sines is 1/2 cosine of u minus v minus cosine of u plus v. If you go digging around enough with these formulas, you really do find that they all kind of come back to the same place, and you could just start with kind of Pythagorean identities and a little bit of geometry, and you can get to all of these different formulas that we have. None of these formulas would need anything very intense to be derived from scratch. Okay. Example 9. Let's see. So we're just gonna practice using these. Express sine of 3x times sine of 5x as a sum of trigonometric functions. If we had more time, if we weren't on a time limit, it would be worth it to go through and take like a whole session and just prove all of these different formulas we're learning. But don't really have time for that. Alright, sine of 3x times sine of 5x. So here what's going on is we've got a product of two sines with different inputs. I'm going to call u 3x and v 5x, and then I'm going to use this formula here. Okay. So sine of 3x times sine of 5x is equal to 1/2 times cosine of their difference, and I gotta make sure I get the order right. So 3x minus 5x minus cosine of their sum, so 3x plus 5x. That's going to be equal to 1/2 times cosine of negative 2x minus cosine of 8x. And cosine is an even function, so it's going to absorb this negative as if it was never there. So 1/2 of cosine 2x minus cosine 8x. So this is coming from the fact that cosine is even, so cosine of any negative input just yields the cosine function. Like x squared, it's even. It's symmetric around the around the y-axis. Right, because if I draw cosine, it's like this, symmetric around this axis. Just like a parabola, so it absorbs negatives. Okay. What can I say? I guess I can distribute the 1/2. That's about all I could do here. I could do a bunch with the 2x and the 8x, expand those a whole bunch, but I think this is fine. I think this is all we need to do. They didn't ask us to get it all the way in terms of just like cosine x. They just said trig functions, so this is probably fine. Okay. That's pretty much how those go. You get a product of two different sines or cosines, and then you just name the two inputs just to keep your work straight, and then just plug into the formulas. Okay. Let's see, now we've got going in reverse sum to product formulas. So now we're going from a sum or a difference. So if I have sine x plus or minus sine y, that will be equal to 2, these are weird, times sine of x plus or minus y all over 2 times cosine of x minus plus y all over 2. So what this means is if I have a sum of two sines with different inputs, then I'll have 2 times sine of x plus y over 2 times cosine of x minus y over 2. So the sign here, the sign meaning the plus or minus, matches in here, and it does not match in here. That's what the minus plus means. And then we've got two different setups for cosine. So we need to split them into two different ones. So for cosine x plus cosine y, we've got 2 times cosine of x plus y all over 2 times cosine of x minus y all over 2. For the difference, we've got negative 2 sine of x plus y over 2 times sine of x minus y over 2. Okay. Okay, and then just an example using these. In my experience, the double angle and half angle formulas are actually and power reducing are the ones that actually come up and you actually use the most. The product to sum and sum to product, in my experience, usually are set up like the problem is specifically written so that you have to use them. Like this one, write sine of 7x plus sine of 3x as a product. That's a 7. Okay, so they're using x and y here. I guess I can say this x from the formula is playing the role of 7x, and y is the 3x. And I'm using this formula with the sum, so I'm going to say sine of 7x plus sine of 3x is equal to 2 times sine of x plus y, so 7x plus 3x all over 2, times cosine of their difference, so 7x minus 3x all over 2. And then 2 times sine of 10x over 2 times cosine of 7 minus 3 is 4x over 2. And now this is still happening inside, so I can say 10 over 2, just 10x over 2 like I would normally simplify that. That's going to be 2 sine of 5x times cosine of 2x. And that's all they wanted. They wanted this sum written as a product, and we've done that. It's now a product. Okay. And let's just, for the last problem, we'll use one of these sum to products formulas to verify an identity. So let's verify sine of 3x minus sine of x over cosine 3x plus cosine x equals tangent x. Okay, so we're going to verify this identity. We're going to verify this identity somehow. Oh yeah, using sum to product formulas. Okay, so we've got a difference of two signs up top. So in the top, I'm going to let x be 3x, which is a bit weird, and y be just x. So, oh, that's actually going to work for both of these. because they're 3x and x in the top and bottom. So for the top, I'm going to have, by the way, I'm working the left hand side here, because there's not much to go on with tangent of x. So sine of 3x is going to be, minus sine of x is going to be 2 times sine of 3x minus x all over 2 times cosine of 3x plus x all over 2. That's in the numerator, and it's minus here because it's minus in there, so those signs should match, and then this one should be opposite. That's why that's a plus. Now on the bottom, I'm going to have sum of 2 cosines, so I'm going to have this formula. So 2 times cosine of their sum all over 2 times cosine of their difference all over 2. And now I just need to simplify, so I'll just do it on the new line here. That's going to give me 2 times sine of 2x over 2 times cosine of 4x over 2 all over 2 times cosine of 4x over 2 times cosine of 2x over 2. Okay, now this is going to give me, these two will, well, the 2's will cancel, and the cosines of 4x over 2 will cancel, because they're exactly the same, and I'm going to be left with sine of 2x over 2 over cosine of 2x over 2, but also those 2's inside each of these will cancel, so I'm just left with sine of x over cosine of x, which of course is tangent of x, which is what I wanted. There we go. So you can kind of see how these problems with the sum to product and product to sum, they kind of have to be set up. They don't seem quite as useful as the double angle and half angle formulas, in my opinion. Okay, that is it for 7.3. Just a bunch of formulas and practicing them. Hopefully you don't have to memorize all of these because it's a lot.